So what we have here today, in very much a top view, is an ice cream maker. So I've popped the lid, did that off camera because you never know how much you're going to have to faff and fiddle with it. But it looks like this. And got your keypad over here. This is the part where the ice cream gets made. There's a beater that goes in like that. And over here is the motor that turns the beater. There's the electrical connections over there. It has a cooling fan on it. And there one can actually see the motor windings. So this sits over there like that, and now it's gone closed, but that's okay. So what happens is you put all your stuff in here, the ice cream mixture, and then you get it going. So what you do, you plug it in and it beeps. And it says 0 power. Screen comes on, it says 60 seconds, 60 minutes. So you can over here set how long you want to make ice cream for. So when you press start, that thing starts beating and the refrigeration starts, so the cooling lighters come on. It says it's mixing and it shows the temperature and the time left. So what I'm going to do is take the beater out before we completely destroy this thing. Set that one side. Now it shows the temperature over there in the remaining time. Now what we have happening inside here, there's your compressor, there's a condenser, there's a condenser fan. It's a fan called condenser. The air is going in that direction, so it's exiting out here. So airflow through it is in that direction. Over there is the power terminals for the beater, and up there is the control board for the micro, which runs this whole operation. So obviously here's your little compressor. This runs on 134A refrigerant. There's the capillary tube over there, and they both go into the drum. The outer part of it is insulated. This over here is a silicon sealing ring between the drum and the cover. So, and over here the process tube where the system is evacuated and then charged with refrigerant. Over here is your dryer, the filter dryer. So the desiccant in there. So that's where any moisture that's in the system gets retained, and any solids also get retained in here. There's a fine mesh screen in the top of that, which stops any solids from getting into the capillary tube, because that would block it, and that's not good. Now over here, these two wires are your temperature sensor for the drum, so they go in with the insulation over there. So what's happening now is this thing's cold. So all the refrigerant is in the compressor's oil. So what is the refrigerant has to boil off, which will happen by virtue of two things: the low pressure inside the compressor on the low pressure side, and the fact that this is starting to heat up, which will put energy into the oil and thus heat up the refrigerant and assist with boiling it off. That then goes out here. This is the discharge tube. Compressor discharges over here. I can feel it starting to warm up, and over here it condenses into a liquid. So this is the high pressure side. So here it's going to condense. You feed into the top of the condenser and liquid comes out the bottom. You don't do it the other way around, because what happens then, if you condense into the bottom of the condenser, it fills up with liquid, so there's no way for the gas to condense because you formed over a liquid barrier. So that's why you condense downwards, so your liquid drains downwards by gravity, and it leaves this largely empty of liquid, so that you've got area, the copper pipe, for the vapor to condense against. So that's very important when setting up a system like this. Don't get it the other way around, because then your condenser won't work. It'll work a little bit, but it works very poorly, and you're going to have high head pressures, which is going to make your compressor unhappy. And it's also going to result in insufficient cooling inside your machine that you're cooling, or your space that you're cooling, or your cabinet, or whatever it is that you're cooling. It's a lesson about condensers. So from here the capillary tube goes to the coil, which is a spiral coil inside here, and it then enters pipe, which is of a thicker diameter. It's this sort of diameter, slightly thicker. It's an aluminium pipe. Now over here you can see that the capillary tube is wrapped around the suction pipe. This over here is called the suction pipe. Okay, so the capillary tube is wrapped around here for a very important reason. When it comes out of here, it's still hot, so you've got energy in your liquid. Now having this tube in contact with your suction line cools it down, because the vapor coming out of here and the tiny last little bit of liquid being boiled off comes out of here. So this tube is cold. So what happens is this liquid, as it goes through here, gets cooled. It's called subcooling. So this has been cooled to a low temperature, much lower than what it was over here. The reason for that is that when it gets into there, that energy that's in the gas doesn't have to get removed by boiling off the vapor to cool down the liquid and then be drawn out as a liquid and part of the refrigeration cycle. You're using leftover cold to cool your liquid before it goes in there. That makes the system more efficient. It's called subcooling, and it reduces what's called flash gas. Now that flash gas is, as the name says, in the last part of the capillary tube. You want the liquid to remain a liquid. If your liquid boils in that last part of the capillary tube, it alters the dynamics of the system, because you're now having vapor trying to travel through a larger vapor traveling through the capillary tube, which restricts the flow of refrigerant. So that's the other reason that you want to keep the refrigerant cold going into the capillary tube, and especially so that it maintains a constant velocity. So those are the two reasons for getting rid of flash gas. Is the energy side of it, and also maintaining the liquid velocity through the capillary tube. Okay, so that's heating up very nicely. This is definitely making cold. I feel that. Let's have a look at the temperature. Minus 36, minus 38 degrees C. Now this thing is getting on. It is getting on with it. That's for sure. So this is going to refrigerate the ice cream mixture, and it's then going to solidify in there. And once the beater stops, then this thing senses that the beater is no longer turning, and it turns off the motor. It works on the motor has limited torque available. It can't just keep going. It definitely is just hardened. So when this hardens, the motor stalls out, and the thing detects that, and it shuts down power supply to the motor in these wires over here. The compressor is a split phase motor, so it's a PTC start, so it's got a start and a run winding. The run winding has a higher inductance in the start winding, so your start winding leads the magnetic field. You have two magnetic fields. The start winding leads because it's more resistive, and the more inductive the run winding lags, produces the rotating magnetic field. That resistor then warms up once the within a few seconds, and current stops flowing through it. So once it's spinning, within a few seconds you're only running on the run winding, and it keeps it going. Also in there is over temperature and over current protection. It's located in there, and it's all inside the terminal block. This is a B43H compressor from Y. It's tiny. I would estimate that to be about a 1/15 of a horsepower. So that is very cold now. You can actually see the ice over there. Be careful I don't give myself frostbite by touching stuff that's very cold. Let's see what the temperature says. Minus 39. It's not going to get much colder than that, because you've actually reached the point where you're starting to go below atmospheric pressure on the suction side of this compressor, and so it's the refrigeration cycle's capacity is therefore much reduced at this point. So it is basically able to maintain that temperature but not cool it any further, because this refrigerant I think boils to about minus 36 at atmospheric pressure. Could be wrong on that, I'd have to check, but we're basically going into a vacuum, so your compression ratio of your compressor has gone up, so therefore you're moving less gas, you're pumping less gas, so therefore there's actually not a lot of heat coming off the condenser at this stage, because this guy's basically already pulled down and it's at temperature. It happens quite quickly, and even the air inside there, it's cold. And I don't think there's much else to talk about here with the ice cream maker. The electronics, it's a little keypad, there's a LCD display and so on. That's fairly straightforward stuff. I think that's just electrical connections and possibly relays and stuff down there. Let me get a mirror and have a look. Let's all have a look. Yeah. I don't know how much you guys are going to see of that. Yeah, there's a relay over there. Right over there. So that's where the hardware is that takes care of the switching of the motors and stuff. They're turning white. That is getting pretty cold. It does look as though this is an aluminium evaporator, because I see that that is an aluminium pipe over there. And internally here, that's where it becomes copper. That's where they join it with the secret sauce. Make it from aluminium into copper. Now, by the time the refrigerant has come all the way to here, there's only gas left. So this pipe is not very cold. And basically it's still fairly cold over here, but your capillary tube over here is removing that last little bit of cold from the gas, or adding heat to it. So basically your refrigerant, after it's boiled, warms up further. It's called superheat. So over here your refrigerant becomes superheated. The temperature of the refrigerant going into here is quite important. The flow and the temperature has got to be right, because that's what's responsible for the cooling of the compressor as well. Is this refrigerant going in here, that's what cools the motor. These motors, apart from the air on the outside of the compressor dome, don't have any form of cooling, so the refrigerant does most of it, and that's quite important for the cooling. So your superheat's got to be right. It's got to be enough to provide cooling. It's got to be enough to provide the right amount of refrigeration in here. So you fill in this evaporator with liquid, but by the time it gets to the top, all the liquid's boiled off. If you've got too much coming back, you'll have liquid going into the compressor, which makes it inefficient and can also cause the oil to foam and get drawn into the compressor, and then it tries to pump liquid, which is obviously bad. It's called liquid slugging, and that ruins the compressor. It washes the oil out of the bearings, it bends the valve reeds, it wears out the piston, and it's bad. That's a common cause of compressor failure, is liquid flood back. That's what it's called. And slugging is when the compressor's mechanical parts ingest liquid which is not compressible. That's equivalent of hydrolocking. So that's the refrigeration cycle. This oil in here is polyester oil. It's a synthetic oil. The reason for that is that standard mineral oil is not soluble in this liquid refrigerant. So what happens if you try to use mineral oil in these modern HFC refrigerant systems, the oil doesn't dissolve in the refrigerant, so it doesn't carry with the refrigerant and cycle back to the compressor. It's called oil transportation. The velocity of the gas in this pipe is important for the oil transportation, but also the oil's miscibility in the refrigerant. So the polyester oil is soluble in this HFC refrigerant 134A, and therefore it gets transported back through here and back to the compressor, because everything inside the compressor is bathed in oil. So therefore some of it leaves through this tube, goes through the condenser, becomes part of the liquid, and goes through here. That's why refrigeration leaks can often be identified by the presence of oil at the site. It's because there's oil everywhere in the system. So that's how the oil works. The way these work, the stator of the motor sits on top, and the compressor parts live further down, so it's a splash lubricated system internally, and there's usually an oil slinger on the crankshaft. It's a reciprocating compressor, by the way. You get different types. You get rotary and you get scroll compressors as well. Those are found in domestic air conditioners, and then in commercial compressors you encounter screw compressors as well. And then on your even bigger systems you get turbo compressors and centrifugal compressors. Those are very, very big machines, massive. Those are thousands of horsepower in size. Big turbo compressors called centrifugals. So let me think, what else can I tell you about this? Look at all that frost. I think that's it. Got the fan over there blowing away, so air moves this way through it, exits through those vents on the side. And so one last look at the screen. 40 degrees C, and the time is 38 minutes, so we have been talking for 22 minutes, and I think that's long enough. You've learnt a lot of things about an ice cream maker in the process. Now this is the beater, the pedal that lives in there, makes ice cream, because you have to stir ice cream while you're freezing it. And then you have your motor over here. There's a shaded pole motor over here, and in here there's a gearbox. There's a reduction on it, so this turns slowly in relation to the motor speed. It's got a little aluminium gearbox housing in the bottom with some gears in it, with some helical gears. No, they're probably straight cut. So that's the motor part of it. I'm not going to take that apart, because that's straightforward. It's just a motor and gearbox inside here. And then there's that. And I think that's going to conclude our talk up here about the mechanics going on inside here. The other type of ice cream maker doesn't have refrigeration. It's just got a aluminium dish. Of course, aluminium has a fairly high specific heat capacity, so you pre-freeze that in your deep freeze for a day. And then when you want to make your ice cream, you pour your mix into here, and you fit the lid with a motor which stirs the ice cream till it's frozen. Then you scoop your ice cream out and you store it in a freezer. So that's a non-refrigerated type of ice cream maker. The advantage with that is that it's cheaper to purchase. The disadvantage is that you've got to put this in the freezer for a day beforehand to make it cold. Now this has an advantage that you can just keep making ice cream all day long. The disadvantage, you've got the cost of the refrigeration system. So there's those two trade-offs. It depends who you are and what you want to do, what your budget is and that sort of stuff. Okay, I keep thinking about things to talk. I love refrigeration because it's physics, thermodynamics. This stuff has always excited me, so it's nice to get to talk about it for once. Maybe maybe not. Okay, ladies and gentlemen, it's time to wrap this up. Thank you very much for being here today, having a look at this with me, seeing what goes on inside. Now everybody knows what goes on in an ice cream maker, you know. The commercial ones just sit sideways on the snow cone machines, but same principle. You got the refrigerated drum with the spiral inside, and it stirs it and makes ice cream. That's how ice cream is made. Okay, thanks for being here. Take care, everybody. Ladies and gentlemen, I'll see you next time for more nice stuff. Alright, cheers.